All right, we're back. We're still on page 5 of notes 13, maybe? Yep, of Calc C. And we're talking about Euler's method. And so we're just doing a lot of practice problems. This problem that we're about to do is actually, so I wasn't really thinking about this. This problem is separable. If you want to go ahead and solve it, you can. And this problem is also separable if you wanted to go ahead and actually solve the differential equation to like check your answer and do things like, it's always good practice. Like I definitely recommend it. And then your calculator can check it if you use differential equation solvers. So try to do them by hand and then see. And then both of these actually use the integrating factor method. So you can solve all of these if you want to. You don't need to, but it's, you should always be practicing. So that's a good thing to practice. All right, let's see if we can do this. So we're going to set it up, and then we're allowed to use a calculator for our calculations, and that's awesome. dy is f prime of xy. I think I'm writing this huge. I mean, I zoomed in, so I can't really tell, but like, it feels huge. It's bigger. All right, here we go. 0 and 2. I say here we go a lot. I say okay, and here we go, and I don't know, probably other things. What are we doing? It might actually help to factor this. So this is y and 1 plus x. So I have to add 1 to the x value, which gives me 1, and then multiply by y. So that's just 2. So that's 1/4. This one, we can do that by hand. So this will be 1/8, and then add it again, you get 2/8, so you're at 1/4. So 2 plus 1/4 is 9/4. And then we're going to do another 1/8 because it's our step size. And we're supposed to do the y value times 1 plus this. So the y value is 9/4. And 1 plus the x value is 9/8. It'd be super nice if anything canceled, but I think everything's in like the wrong spot for that. So this is not super great. This is 81 over 64 times 4, so 256. Oh boy. So what's 4 times 64, obviously. 64 times 9. What's 64 times 9? 64 times 9. Feels like there's a thing I can do here, because this is what, 8 squared, and this is 3 squared. So really I'm doing 24 squared, which is 576, I think. So I think it's 576 plus 81 over 256. I mean, I'm not going to know it anyway, so I don't know why I'm bothering with this, but I'm going to keep bothering. So 576 plus 81. Also, there's not like a billion things to do in this video, so I'm going to waste your time doing these calculations. Might be 657 over 256. Should I try to get a decimal by hand? No, I shouldn't have done any of that by hand. So let's say y of 1/4 is approximately 657 over 256. I think that could also all be wrong. Calculator, let's do it. Let's see if we can remember the syntax. All right, so I'll start a new document. Let's not cheat. Okay, so new document, calculator, we want Euler. I mean, I'm just going to cheat because I have a screenshot of what to do, but I don't want to cheat, y plus x times y. Okay, x, y. X is going to start at 0 and end at 1/4. Y is going to start at 2, and then my step size is 1/8. I think that's right. Let's see. And then let's see if 657 over 256, over 1, I guess. Yes. So we got it. Nice. Good job, us. That killing it on arithmetic. What more could you ask for? All right, let's switch back to the notes so that we can, I don't know. Oh, I mean, there's another problem or another idea. It's actually a really, really important idea that we've talked about, right? Where does Euler's method come from? It comes from writing a tangent line, moving a tiny little bit along the tangent line, doing a new tangent line, move a tiny little bit, new tangent line, tiny little bit. So the concavity of your curve must have something to do with whether or not you're getting an over or underestimate, because the concavity tells you where the tangent line is. If the tangent line is always below, you're going to get an underestimate. If the tangent line is always above, you're going to get an overestimate. So that's basically the idea here. If the curve that we're dealing with. So if for some reason you know the curve is concave up or concave down, you've like examined the second derivative, or maybe you're given a graph, or you're just outright told that. If the curve is concave up, then your tangent lines are always going to be below, and so you're going to get an underestimate. Now, if it varies, which like it never will, but if it varies, you don't actually really know. And if it's concave down, your tangent lines are above, so you're going to get an overestimate. And I would say this type of question is almost just as common as the question about like a tangent line. Does a tangent line give you an over or underestimate? It's like, oh, what's the second derivative? Second derivative is positive, curve's concave up, tangent line's below, underestimate. Same logic, same thought process. So concave up, you know, you would maybe like start out knowing this, and then you go like tangent, and then like a little tangent, and then a tangent, but you're definitely below. And then concave down, I don't know, maybe you start here and you go your tangent a little bit, and then another tangent, and then we're turning the corner here. That's not even a line. Wow, I'm struggling there. I don't know why. And then like there, perhaps. Overestimate, like no question. So think about the concavity. I always like, you hear me do it, so I think like I need to know about concavity. I need the second derivative. The second derivative is negative. That means that the function is concave down, which means the tangent line is above, which means you're going to get an overestimate. Like I just run through the whole thing. You can do that. I would like to think there's nothing wrong with that because it's the way that I do it. So all right, I'm going to stop this here. I feel like this might be a short video, but that's okay. We'll be back in the next one to do more. So see you there.